Good afternoon. Welcome back. Hope everybody had a nice Thanksgiving break. Just looking into the Test 4 review handout set, and I had given this worksheet portion out last week, and just looking into what we have, and I'll tell you what, we're going to start off with just the change of base portions, okay, that we have from the first part, beginning with number 3. And we're looking for the approximation, okay, of the base 5 logarithm of 26, and just referencing what we have. Again, we have with the change of base formula. Okay, so if we have a base A logarithm of m, again, if you don't have identity between A and M, and you don't have it in your calculator to be able to evaluate, or if there's not a perfect match between M and A, where M is going to be an integer power of A, what you can do is that you can rewrite this statement in terms of a ratio of logarithms in the same base, where we have the base B logarithm of M is divided by the base B logarithm of A. And for the base B logarithm, you can either put this in terms of the natural logarithm of M to the natural logarithm of A, and also you can use, instead of natural logs, you can also go with base 10 logarithms. And the log of M, log, again in reference to base 10 logarithms, you have with respect to that of A. And for what we have in the case of item number 3, okay, so again we're looking at the base 5 logarithm of 26. Okay, so we have A is represented by 5, M is represented by 26, and you can either take the natural or the base 10 logarithm ratio, okay, and we'll just go with ln for this one. Okay, so we have the natural logarithm of 26 divided by the natural logarithm of 5, and again you have to enter ln twice, once for 26, and after pressing the division key, you have the natural logarithm of 5. And if we round to the nearest 3 decimal places, okay, this will come out slightly over 2 to right at 2.024. And for what we have in the case of the next change of base item, now we got a base 7 logarithm of a fraction, but we have the fraction to be 19/13. So we have, the base 7 logarithm of 19/13, and again you can go with ln again, or you can go with the base 10 logarithm, and we'll go with base 10 log this time around. Okay, so your M is represented by 19/13, and A is represented by 7. And looking at what we have in the follow through, and if you have like certain TI models in terms of how this might look, okay, you have log, again base 10 logarithm, so like 19/13. Again we have divided by the base 10 logarithm of 7. Okay. And for what we have in this particular outcome, okay, this is going to be a lower number in comparison to the result that we had in number 3. And this one is going to come out to just under 2/10, and where we have rounded to the nearest 3 decimal places, this will come out to about 0.195. Alright, now for what we have in the case of the next item, okay, so we still have single terms, and this time we're going from base 5 to base 7 to where we have now the base 3 logarithm, and we're taking that of 38/3. And for this expression, okay, so you have A is represented by 3, M is represented by 38/3, and it could repeat the use of base 10 logarithms, but we'll go with natural log. So the natural logarithm of 38/3, okay, and we have over the natural logarithm of 3. Alright, and in terms of a calculator layout, okay, so have the natural logarithm of 38/3. And we have all over, okay, the natural logarithm of 3. For what we have in this reduction, okay, so you have a little bit over 2.3, okay, and to the nearest 3 decimal places, this will come out to about 2.311. Alright, so this is what we have with individual logarithmic base terms. Now for number 6, okay, we have a bit of a new dynamic, where we have not 1, not 2, but 3 terms that are in the mix. And for what we have in the case of number 6, okay, so we have 3 base 54 logarithmic terms, and we have addition and subtraction in the mix. Okay, so we'll blend in together the change of base formula as well as the condensing counterpart to the sum and difference formulas we encountered the other week. And looking at what we have in the mix, so all these terms are in the base 54 logarithm. Okay, and so we're looking at the base 54 logarithm. Okay, so again, that was 10, and we have yeah, 19. You know, have base 54 logarithm of 10 at the end. Okay, so the base 54 logarithm 19 plus the base 54 logarithm of 25 we have minus the base 54 logarithm of 10. Okay, and looking at determining the value, okay, what you want to do is go ahead and combine as one consolidated base 54 logarithmic term. Okay, now again, you have addition and multiplication implying each other, and then you have subtraction and division also implying each other, and going in the direction of compiling together. Okay, so we have working with the attachments. Okay, so you have first 2 terms are positive base 54 logarithmic terms, and so we have the attachments will go in the numerator, and they're going to multiply each other. And with the base 54 logarithm of 10 being subtracted, okay, this subtraction implies that we will have division by 10. Okay, so you have 19 times 25 will be 475, and we have divided by 10. Okay, so we have a base 54 logarithm of 47.5. And looking at what we have and following through, and again, you can either use natural or base 10 logarithms. Okay, so you have the natural logarithm of 47.5 divided by the natural logarithm of 54 and to the nearest 3 decimal places. This will be about 0.968. Okay. All right. Now, looking at what we have for the next group, and talking about the addition and subtraction properties that we have concerning what we have among the properties of logarithms. Okay, and we have beginning with what we have for number 7. Okay, and we have for that particular group. All right, and what I'm going to do here, okay, is that for 7. Okay, notice we have in both the numerator and denominator the presence of radicals. And what I'm going to do here to put this in the context or within the framework of what we have had with the addition and subtraction, and also working with conversions between exponents and coefficients, I can just rewrite number 7, okay, where we can express the radicals as non-integer exponents. Okay, so for number 7, so we have a base 3 logarithm. So we have in the numerator, okay, so we have x squared. All right, now for the cubic root of y to the 5th, okay, if I write this as a non-integer exponent, okay, so y is going to be the base, and you'll be looking at dividing the inside number, that is the exponent, by the radical index. So the cubic root of y to the 5th, that's going to be y to the 5/3. And for the 6th root of z, this will be like the 6th root of z to the 1st. And as a non-integer power, okay, we have z raised to the 1/6. And for 9 times the 4th root of b, okay, so for the 4th root of b, okay, so we have b raised to the 1/4. Okay, so after the rewrite, okay, from radicals to non-integer exponents, okay, we can look at expanding what we have in terms of positive and negative logarithmic terms, and simplifying, okay, where possible. Okay, now again we have with our 5 factors, okay, we have 3 at the top, 2 on the bottom. Anything at the top, okay, once we itemize, we'll have positive terms in the base 3 logarithm. Okay, so you have x squared is at the top. Okay, so you have the base 3 logarithm of x squared, y to the 5/3. We'll take care of what is at the top first. Okay, so you have the base 3 logarithm of y to the 5/3. And we have plus the base 3 logarithm of z to the 1/6. Okay, now for what we have in the denominator, okay, we have 9 and b to the 1/4. Okay, so 9 is on the bottom, so that expression will be subtracted. Likewise for b to the 1/4, that will also be subtracted. And looking at converting the exponents to coefficients. Okay, so I have x to the 2nd, so 2 will be at the front. For the next term, 5/3 to the degree will become a coefficient. And we have 1/6 will also become a coefficient. And for different reasons, okay, we'll have a conversion for the base 3 logarithm of 9, and we'll get to that in a moment. And then we have with b to the 1/4, 1/4 will be placed at the front. And now for the base 3 logarithm of 9, this expression can be converted to a constant, and the reason for this is that with 9, okay, relative to what we have for the logarithmic base, Okay, 9 is a multiple of 3, but it is also an integer power of 3. Okay, so 9 is going to be the base 3 logarithm of 3 to the second. Okay, so that is going to go to 2. And for what we have in the follow through, okay, so first term, okay, so we have 2 times the base 3 logarithm of x. We have followed by, okay, 5/3 of the base 3 logarithm of y. And then we have plus 1/6 of the base 3 logarithm of z. Okay, now base 3 logarithm of 9, the subtraction of that is going to be the subtraction of 2. You have minus 1/4 of the base 3 logarithm of b. Okay, and so those will be your 5 terms that we have. Okay, it doesn't have to be in that order, but as long as you got for the terms of x, y, and z, as long as those are positive, and what we got with the constant 2, and for what we have with the attachment at b, okay, those are supposed to be negative terms. All right. Now, also we have a bit of a rewrite, and we have for the case in number 8, okay, there's one portion here, and we have for number 8, okay, so you have base 5 logarithm of 7x squared y cubed all over w to the 4th times the square root of z squared plus 5. So we have one radical, and I can go ahead and rewrite this one. Okay, so I have 7x squared y cubed. We have all over w to the 4th. And for the square root of z squared plus 5. Okay, so I can write this as z squared plus 5 quantity to the 1/2. And then for what we have in crossing over to writing as sums and differences of logarithms. All right, and have a little bit of history to repeat in one context. Okay, we got 3 factors in the numerator, 2 in the denominator. And taking what we have now, okay, so we got 7 at the front. Okay, so I'm going to have the base 5 logarithm of 7. Okay, we have x squared. Okay, so we'll look exclusively what is at the top first of all. Okay, so we have plus the base 5 logarithm of x squared and I have plus the base 5 logarithm of y to the 3rd. Okay, and we have our expressions in w and z on the bottom. Okay, their respective logarithmic terms will be negative. Okay, so we'll have minus the base 5 logarithm of w to the 4th and minus the base 5 logarithm. Okay, we have a z squared plus 5 to the 1/2. Okay, and looking at converting the exponents to coefficients, okay, so we can x squared and the 3 and y to the 3rd. Also for what I have in w, and also for what was originally the radical expression in the variable z. Okay, now we have with the first term, okay, expressing in exact terms. Okay, now unlike what I have with the base 3 logarithm of 9, we have for the base 5 logarithm of 7, okay, the attachment is not going to be a multiple or integer power of the number representing the logarithmic base. So 7 is not a multiple or an integer power of 5. So this first term remains fixed. Okay, so I have the base 5 logarithm of 7. Okay, then we have plus 2 times the base 5 logarithm of x. Then we have for the rest, we have 3 times the base 5 logarithm of y. We have minus 4 times the base 5 logarithm of w. And finally, we have minus 1/2 of the base 5 logarithm of the quantity of z squared plus 5. And that will be the result in this case. All right. And we'll eventually look into number 9. But for what we have in terms of the in the flow of things, okay, if we go ahead and look at combining terms as a single logarithm. Okay, so we have for number 10, okay, we're looking at taking what we have here. So you have 2 times the base 5 logarithm of 10 plus 3 times the base 5 logarithm of x. And we have minus 2 times the base 5 logarithm of y. Okay. And just looking at what we have here. So I'm going to make this into a single base 5 logarithmic term. Just go ahead and copy this. Okay, so again we have for part of the process, okay, we're looking at again compiling together as a single logarithmic term. Okay, in the expanded form, expressing as sums and differences of logarithms that took exponents and wrote as coefficients, but going the other way. Okay, and now converting from coefficient to power. So I want to get kind of clean up in terms of not having any coefficients explicitly in front of the logarithmic terms. Okay, so we got, first of all, we have the base 5 logarithm of 10 squared. Okay, and then we have plus the base 5 logarithm of x cubed. We have minus the base 5 logarithm of y squared. Okay. And again, we have multiplication implying addition and vice versa, and division implies subtraction, and also works the other way. So for what we have here, I've taken care of the coefficients, and all the terms are in base 5 logarithm. And looking at putting together, okay, and once we write, okay, in factored form, okay, so we got 10 squared, and that is originating from a positive base 5 logarithmic term. Any attachment from a positive logarithmic base term, we have in the numerator x cubed, we have originating from positive term, and we have y squared comes from a negative base 5 logarithmic term, and so that will go to the bottom. Okay. Okay, now if this were your final answer, I mean, I personally would count it correct, but know how nitpicky sometimes Alex can be. You want to go ahead and just write out explicitly what the number is in the case of 10 squared. So 10 squared, we have a couple of 10s multiplying each other. Okay, so this will come out to 100. Let's have 100x cubed all over y squared. Now, looking at what we have for number 11, okay, and this one, you can express the result in either of two ways. Okay. Now for 11, okay, so you got some coefficients out at the front. Okay, so we got 2 times the natural logarithm of u. We make that into an exponent. Do the same thing with 3. Then for the third term, okay, we have 1/2 as an exponent, and we have 3/4, okay, which we'll be looking at converting as an exponent as well. Okay, so for what we have in the layout, okay, so we have the natural logarithm of u squared plus the natural logarithm of v cubed, plus the natural logarithm of u plus v raised to the 1/2. We have minus the natural logarithm. We have the w to the 4th plus y to the 5th minus z raised to the 3/4. And looking at putting together as a single natural logarithmic term, okay, so we have the first 3 terms, okay, those can be positive, so the attachments go in the numerator. So we have u squared, v to the 3rd, times u plus v raised to the 1/2, and with the last term being subtracted, okay, that attachment is going to go in the denominator. Okay, so we've got the quantity, so you have w to the 4th plus y to the 5th minus z raised to the 3/4. Okay, and that's one way you can express your final answer. But I have seen some do like a handwritten test, like express the powers as radicals, and that's another option. And in terms of how that will look, okay, so I have u squared, v to the 3rd, and u plus v to the 1/2. This will be taking the square root of u plus v, and for expressing 3/4 as a radical, now again, for a non-integer exponent, okay, the denominator defines the type of radical. So we're looking at a 4th root and this will be of the quantity of w to the 4th plus y to the 5th minus z raised to the 3rd. And you can express this again in either of two ways. And again, we'll be looking at sums and differences of logarithms throughout, especially as we go out, not only in terms of combining logarithms, but also looking at exponential and logarithmic equations. And okay, now from what we looked into last time, okay, just like number 9, we'll eventually look into number 12. I just want to pick up where we had left off in the case of exponential equations. And we start out with those that share a common base. Alright, so just kind of picking up, okay, in what we have in this particular realm, okay, there'll be those exponential equations with a common base, and there'll be also those equations that do not share a common base. And let's say that if you have, for instance, okay, if you're looking at, let's say, solving for x, so we have in the first case, right? We'll say we have 27 okay, to the x plus 2 is equal to 9 raised, okay, to the x minus 3. Okay, so you have the variable x this time on both sides of the equation. Okay, now there's going to be a common base between 27 and 9. Okay, neither one appears yet. Now between the bases, now 27 is a multiple of 9. However, 27 is not an integer power of 9. Okay, then you have like 9 to the first is 9. But 9 to the first is 9. But if I go to 9 to the second, 9 squared, again, it's going to be 81. So where we have a common base, okay, so if we scale back, and you want to have looking for a number that can multiply itself into both 9 and 27, and that common base, okay, it's going to be at 3. Okay. Right. So taking 27 and 9, if I rewrite in terms of base 3, we want to have 27, okay, that's going to be 3 cubed, and for 27 to the x plus 2, in line with base 3, you have 3 cubed raised to the x plus 2 power. And for 9 raised to the x minus 3. So 9 is going to be at 3 squared. This will be to the x minus 3. Alright, and now we have a exponential base is 3. We have both of them each. Okay, we have raised to a power and then raised to another power. And we have with the power property, okay, in terms of what to follow through with, namely the power property, you'll be looking at the exponents and multiplying each other. So on the left you have 3 raised to the 3 times all of x plus 2, and we have to the right we have 3 raised to the 2 times all of x minus 3. Okay, all right, so we have our single base 3 terms. Now for what we have on the left, okay, we have 3 raised and 3 over x plus 2, so that's going to be 3x plus 6. And for what we have on the right. 3 raised and 2 times the quantity of x minus 3. So this will be 2x minus 6. Alright, so I have single base 3 terms on both sides, and I can set the powers equal to each other. Okay, so now I have 3x plus 6 is equal to 2x minus 6. Okay, and I can join together the variable terms. Okay. So I just take out 2x and have x terms on the left and everything else on the right. So I move the 2x and I can move the 6 from the left upon subtracting. And so combining our variable terms, okay, so we have 3x minus 2x becomes x. And we have negative 6, and then take away 6, and we come out to negative 12. Okay, so we have that x is equal to negative 12 in this item. Okay, and we started out with single exponential terms. Okay, with unlike bases, and we had to scale back to rewrite in terms of a common base. Now, let's say that if we have multiple terms on either side of the equation, and we'll say that we have, for instance, okay, we'll say we have like 8 to the x minus 2, and we'll say we have times 4 to the 3x. Is equal to 16 raised to the x plus 5. Alright. Now, if we had, let's say, just 4 to the 3x and 16 to the x plus 5, you would have 4 as a common base. But with the 8 present at the front, okay, it kind of throws a different twist. Okay, now 16 relative to 4 is both a multiple and an integer power, whereas in the case of 8 relative to 4, 8 is a multiple of 4, but it is not an integer power of 4. Okay. And so just like what we did with 27 and 9, if we scale back and identify the common base, that is a number that will multiply itself throughout into 4, 8, and 16, then we'll have the number 2. And just re-expressing 8, 4, and 16 in terms of base 2. Okay, now 8. Okay, now 8 is 2 times 2 times 2. So 8 is 2 to the third. And for 8 to the x minus 2, in terms of base 2, initially you have 2 cubed to the x minus 2. And for 4 to the 3x, now 4 is 2 to the second. And 4 to the 3x, we're going to have 2 squared raised to the 3x. And for 16 to the x plus 5, okay, so 16 is going to be 2 to the 4th. And it's going to be taken to the x plus 5 power. And okay, so we have going into the next stage, okay, we're looking at the power property of exponents. Okay, so we have with the first base 2, we have 3 times the quantity of x minus 2. We have with the next, okay, so we have the base 2. Now we need the parentheses this time around. Okay, so we have 2 raised, and this will be 2 times 3x. And for 16, then we have 2 to the 4th raised to the x plus 5. Again, just multiplying the exponents together. Okay. All right, so 8 to the x minus 2. This will translate out to 2 raised to the 3x minus 6. Let's see, add that x. All right, so for 4 to the 3x, again, 4 is 2 squared, to the 3x, and then base 2 raised to the 2 times 3x, so this will be 2 to the 6x, and then for 2 to the 4 to the x plus 5, multiplying the exponents, so this will be 2 raised to the 4x plus 20. Okay, now we have all of these as base 2 terms. Okay, now I have on the right a single base 2 term. Now to the left I have a couple of these, but I can piece together as a single base 2 term. Now while I wish it was a name other than the product property, that's what it's called. And the product property is going to be looking at combining the powers this time by adding. Okay, and so we have making into a single base 2 term on the left. So we've got 2 to the 3x minus 6 plus 6x we have is equal to 2 raised to the 4x plus 20. And for the left hand side, okay, quite a bit of activity happening and putting down as a single base 2 term. So we've got 3x plus 6x is going to be 9x and minus 6. And to the right again, you have 2 to the 4x plus 20. And now that we have single base 2 terms at this stage, it took more steps than what we had in the first example, getting it to single base 3 terms. I can now set the powers equal to each other. Okay, so you have 9x minus 6. Is equal to 4x plus 20. Okay, so you have like terms on opposite sides. Okay, so got 9x and 4x. I'll just take care of the smaller variable terms. So I'll take 4x away. Have the x terms on the left, and it'll move 6 by adding. And so here we have 9x minus 4x, so this will be 5x. And we got 20 plus 6, okay, so this will be 26. And upon division by 5, okay, you can write it as a fraction. So we have 26/5, and also since we have a complete decimal or an ending point or location, we can also write that as 5.2. Okay, so in the first case you have the power property of exponents. Second case, all right, have a blend of the power property as well as the product property. And then there's another scenario. Okay, we have another common property. Okay, this is one that involves fractions. And let's say if we have like 1,000, taking the reciprocal of it. Okay, so we have 1/1000th. Then we have to the x minus 1 is equal to 10 raised to the 2x plus 1 degree. Now for this one, okay, unlike the first two scenarios, I already have the common base to appear, and that's going to be with the number 10. And we have the right hand side of the equation already expressed in terms of the base 10. Okay. Now for what I have on the left, we had to adjust. Now I had the reciprocal of 1000. Now 1000 is both a multiple and an integer power of 10. Okay. We have like, okay, 10 times 10 is 100. 100 times 10 is going to make 1000. So 1000. Okay, that's going to be 10 to the third. Okay, now I've got the reciprocal of 10 to the third. Okay, but if I rewrite in direct fashion, okay, I can look at the inverse rule. Okay, this basically states that for, say, the reciprocal of a base to a power, like if I have 1 over x to the m, this would be x raised to the negative m. So making this type of transition with the inverse property. Okay, so you have like 1 over 10 cubed. This would be 10 to the negative 3. So we have re-entering, okay, the power property. Okay, so we have 10 to the negative 3 times all of x minus 1. Okay, now I still have to the right, still sitting, okay, I have 10 raised to the 2x plus 1 degree. Alright, now for what we have on the left, okay, so you got 10, negative 3 times the quantity of x minus 1. Okay, so this will be 10 to the negative 3x plus 3. Is equal to 10 raised to the 2x plus 1 degree. Okay. Now I got single base 10 terms, both in terms of directly base 10. And so I can now set the degrees equal to each other. Okay, so I have negative 3x plus 3 is equal to 2x plus 1. And just combining the terms. Okay. And what I'll do here, I could move the 2x over, just have the x expression on the left. What I'll do here, just to take out the smaller variable term, it's going to move the 3x. And just momentarily have the variable terms on the right, and then taking the constants, combining them on the left. So we have, upon subtracting 1, okay, so 3 minus 1 is 2. And 2x plus 3x is 5x. So 2 is equal to 5x. And we have a division by 5. Okay, so we have 2/5 is equal to x. And so we have for our solution in x, so the x is equal to 2/5. And just like in the case of 26/5, okay, we also have a terminating decimal, and you can also write this as a decimal at 0.4. So you have a blend of the power and the inverse rules, and tell you what, just for the next few moments. Okay, tell you what, let's see what we get in terms of solving for x. Say we have here, we got 1/8 to the x minus 2 is equal to, say, 2 to the 2x plus 1 times 16 raised to the x power. Okay, now for this item, we'll have a bit of a blend of the inverse rule, as well as the power property, as well as the product property of exponents. So this one is a little bit tricky. And for what we have here, again, we have 1/8 to the x minus 2 is equal to 2 to the 2x plus 1 times 16 to the x. Okay. And we have the common base present, okay, with the number 2. And just setting things up, okay, in terms of base 2. Now the left hand side, again, we have the reciprocal of 8. Again, 8 is going to be 2 raised to the 3rd. So right now we've got 1 over 2 cubed raised to the x minus 2. It's equal to 2, okay, which is already present, so we have to the 2x plus 1. Now for 16, okay, now 16 is going to be 2 raised to the 4th. And again, just like with the reciprocal 10 to the 3rd, which I had as 10 to the negative 3, I have with the inverse rule, the reciprocal of a base to a positive power will be the base to the negative of that power. So 1/8, okay, we have it 1 over 2 cubed, but in direct terms, with base 2, this will be 2 to the negative 3. Okay, to the x minus 2. To the 2x plus 1. Now for 16 to the x, I have 2 to the 4th to the x. And if I just multiply it together, well, this would just be 2 raised to the 4x. Okay, so for what I have on the right, okay, I have a couple of base 2 terms that I can piece together as a single base 2 term. But for what I have on the left, okay, I'm looking at multiplying the powers together. Okay, so I have 2 to the negative 3 times all of x minus 2. And to the right, we have 2 raised to the 2x plus 1 plus 4x. And for what I have on the left, okay, so we have 2 to the negative 3x plus 6 is equal to, we have 2, and we got 2x plus 4x will make 6x. We got plus 1. Now I have single base 2 terms on both sides, so I have the capacity to set the powers equal to each other. Okay, so we have negative 3x plus 6 is equal to 6x plus 1 And once again, combining like terms, so I'm just going to take out the smaller x term, which in this case is going to be minus 3x. So I'm going to add 3x. And just have the x terms on the right hand side. Just move the constant 1 over by subtracting. Okay, so about 6 minus 1 is 5. And 6x plus 3x will make 9x. And we have with division by 9. So 5/9 is equal to x. So we have for the solution that we have for x. Okay, this will be a fraction that does not have a terminating decimal. And so we have inexact form. Okay, so we have that x is equal to 5/9. And again, these are cases of what we have for equations that share a common base. Now, as a bit of a segue to the other type of exponential equation, okay, there are two categories essentially for exponential equations when they do not share a common base. And the first type we're going to be looking at, and this will be reminiscent of the first property of logarithms. Okay. And we have just serving, again, as a backdrop case. So we have just with our properties of logarithms. Again, whenever we have a match between the logarithmic and exponential base, we have the exponential base is raised to a power where we have the base a logarithm of a to the x reduces to that power. And again, we have with the change of base formula, again, we can put in terms of ratios of natural or base 10 logarithms. And let's say that if we have just as like a couple of quick examples. Say if I'm looking at solving for x. And say we have in the first case, right? So we have like 4 to the x is equal to 39. Okay. So you're looking at the degree x. Okay, so whenever you raise 4 to it, okay, it comes out to 39. And just like anticipating what the value of x might be. Okay, now, so you have like 4 to the first is 4. 4 squared, or 4 times 4 is going to be 16. But once we get to 4 cubed, guess what? We have 4 times 4 is 16 times 4, and 4 cubed is going to be at 64. Okay. But with the number 39, okay, now it's greater than 16 but less than 64, so we can anticipate that whatever power we have for x, it's going to be 4 to the 2 point something. And we can approximate about what x is going to be. Okay. So looking at what we have with 4 to the x equal to 39. and we use, say, this property here. Since I have x on one side of the equation, I can get the left-hand side converted to x. So I can take this property by taking the base 4 logarithm of both sides. So for the base 4 logarithm of 4 to the x, left-hand side, this will go to x. So I have that x is equal to the base 4 logarithm of 39. And I can follow through with either the ratio of natural or base 10 logarithms. So the base 4 logarithm of 39, so here a is represented by 4, and 39 represents m. We'll go with natural log on this one. So I have the natural log of 39 all over the natural logarithm of 4. And say if we take to about the nearest 3 or 4 decimal places, okay, we have x is going to be about 2.6427. Again, that's an answer to the nearest 4 decimal places. And if you're to take 4 to that power, it's going to be a number very, very close to 39. And again, any discrepancy is just due to the rounding error. Okay. And let's say that if I have, let's say we have 100 to the x is equal to 15. Okay. All right. So here we have the exponential base on the left is substantially larger than the constant that is to the right. Okay, so something we might anticipate. Now, okay, now 100 to the first is 100. Now 100 is a non-zero number, and if you have a non-zero number to the 0 power, that is equal to 1. Okay. And 15 is going to be somewhere between 1 and 100. And whatever we have for x is going to be some decimal value that is positive, but less than 1. So if we kind of work the 100 like we did with 4 and 4 to the x and converting as x. Okay, so just using our base a logarithm of a to the x. Okay, this time we have a is represented by 100, so I can take the base 100 logarithm at both ends. Okay, so base 100 logarithm of 100 to the x. Okay, so this will go to x. And x equal to the base 100 logarithm of 15. And again, I can take the ratio of either natural or base 10 logarithms. Okay, so if I take the ratio, ln will work. Okay, but if I go with just log, base 10 logarithm of 15, we have divided by the base 10 logarithm of 100. Okay, so for that decimal, okay, that is positive, but it's going to be an amount that is less than 1. We have, say, to about the nearest 3 decimal places. We have the x is going to be about 0.5 88. And we've had a lot of interchanging between logarithms and exponents, and just want to sort of cap off, okay, with a business application, okay, where we had worked with like principal rate, time, and where the continuous activity led to the natural logarithmic base e. Okay, and for this next part, okay, now the formulas we looked at had concerned one-time investments. Let's say if you have a repeating investment, this is going to cross over to what we have in the case of annuities. I'll give you just a definition as well as a brief intro. Okay, and if you have you're still working with like P, R, N, and T. Let's say that if you have for a fixed amount P, and say deposited or invested, say n times a year, at the end of each cycle, into an account. That's going to compound interest. Also n times a year. So you're going to have the depositing frequency as well as the compounding frequency to be the same. Okay, and for the future value, okay, now the formula is going to look like an augmented version of what we have had with one-time deposits. Okay, so we have P times, and so we have the quantity of 1 plus R over N to the N times T minus 1 times N over R. Okay, and we'll give you just a case here. Say if I had that P is equal to $300 at the end of each month. And we have, let's say that the account is going to draw interest at 6%. And N, okay, have 12 times a year. So you're looking at monthly compounding, monthly depositing. And we'll look at the value after 5 years. Okay, so you got this formula. Okay, so just filling in for the numbers. So you have P, you have $300 a month at the end of each month. This will be done like 12 times a year, like $3,600 a year. And you got 1 plus R over N. So R, we have 6% as a non-percent decimal. So you have 0.06. You have over N, so that is going to be 12. And for N times T, you got 12 times 5. Okay, we have minus 1. And for times N over R, N is at 12. And R is going to be at 0.06. Okay. And then where the sort of the number crunching begins. Okay, so inside the brackets, now the sum is going to be 1.005, and 12 times 5 is 60. So you have compounding 12 times a year for 5 years. So you have 60 compoundings altogether. You got minus 1. Now 12 over 0.06, that ratio is 200. And for 1.005 to the 60th, okay, that's the number that's going to be over 1.3. Okay, so we're taking away 1. Alright, so we have weighting. Okay, so we got the principal monthly applied at the end of each cycle at $300. And for the activity inside the brackets, now the difference we have it 0.3488 88501. You have times 200. And once you multiply the numbers together, okay, so if you think about it, $3,600 a year for 5 years, that's going to be $18,000 plus the 6% interest that's going to be accumulated. And that's going to be just over another $2,900. So for the future value, you're looking right at $20,931.01. Okay. So wherever you have repeating deposits on a consistent basis, where the depositing frequency and the compounding frequency are the same, you're looking at annuities.